Hello, ladies and gentlemen. Welcome back. We're going to continue with Chapter 6 on Probability and Simulation, the study of randomness. All right, so we're still on Chapter 6.2, Day 2. So here we go. All right. So on page 426, it talks about rule number 5. Remember, we already went over those 4 rules. Okay, pause a moment and see if you can remember the 4 rules. All right, the 5th rule is the multiplication rule. 2 events A and B are independent if knowing that one occurs does not change the probability that the other occurs. If A and B are, again, independent is very, very important, okay? Then you can multiply those together. Notice we have the word and in the middle. The probability of A and B is the probability of A times the probability of B. Okay, that's the multiplication rule for independence. Now, caution, caution, caution. The multiplication rule applies only to independent events. You cannot use it if events are not independent. Keep that in mind. It only works, remember what independent means. One thing does not influence the other thing. Okay, one does not influence the other. All right, so a quick example of this. So the probability of flipping heads on a coin is 1/2, right? The probability of rolling a 4 on a die is 1/6. So if I ask you, those are independent because flipping a die and rolling, or flipping a coin and rolling a die, they don't affect each other. So the probability of heads and rolling a 4 is simply going to be 1/2 times 1/6, which is 1/12. Okay, that's a real quick example of that. We'll see some more of that here in a bit. All right, now, remember we talked about this earlier in the chapter 6.1, or the first part of 6.2. Disjoint events, also known as mutually exclusive. That's where the 2 events are separate. All right, so if we're looking at a Venn diagram like event A and event B, okay, they are totally separate, they are disjoint. All right, so we're going to see some more of that in the future, so keep your eyes open for that. Now, another caution that I want to point out, ladies and gentlemen, the multiplication rule holds if A and B are independent but not otherwise. The addition rule, the probability of A or B, holds if A and B are disjoint, but not otherwise. Resist the temptation to use these simple formulas when the circumstances that justify them are not present. You must also be certain not to confuse disjoint and independence. Disjoint events can't be independent. Ooh, that is so huge. Write that down, highlight it. Disjoint events cannot be independent. All right? If A and B are disjoint, then the fact that A occurs tells us that B cannot occur. If A occurs, we know that B can't occur. That's not independence, folks. Okay, they can't be independent. Look at figure 6.4 on page 419, okay? Unlike disjointness of complements, independence cannot be pictured by a Venn diagram because it involves the probabilities of events rather than just the outcomes that make up the event. All right, we're going to go ahead and look at some examples of probability. If you want to print this off, there's a PDF right above this video. All right, so here we go. So in this case, we've got 3 spinners, A, B, C, and 1, 2, 3. Hey, A, B, C. As easy as 1, 2, 3. Okay, never mind. All right, how many outcomes are possible? All right, remember that is the multiplication rule. All right, how many outcomes are possible? Well, there are 3 possibilities for this spinner and 4 possibilities for that spinner. So 3 times 4 means there are 12 possibilities. All right, list all the outcomes. All right, well, that's not that hard to do, folks. It's only 12. So if I do this as a sample space, remember I do it like this. So that would be A1, A2, A3, A4, and so on. Again, if I go too fast, pause, rewind. All right, so the next question is, what is the probability of spinning an A3? Well, there's only one A3 out of 12. What's the probability of spinning a C? Okay, well, you can just look at the first spinner, folks. You don't even need to look at the second spinner. So the probability of spinning a C is 1 out of 3. A or B? Okay, well, there's one A and there's one B, so that's 2 out of 3. Again, you don't even have to look at both spinners. You can just look at the first one. And then the last one, same thing. The probability of a number greater than 2. Okay, well, that would be the 3 and the 4, right? Which is 2 out of 4, but always reduce. So that's a half. You certainly could look at your sample space up here, okay, but really it wasn't necessary because we can look at those spinners separately with those questions. All right, moving on. A college professor tells his class on the first day that there will be 3 tests in his class and 2 projects. He goes on to tell them that only 50% will get an A on the first test. Okay, I'm going to do some highlighting here. 40% will get an A on the second test, and 30% will get an A on the third test. Okay. Then he goes on to say 70% will get an A on the first project, 20% will get an A on the second project. I've had professors like this. All right. So then the first one is, well, what's the probability of getting an A on all 3 tests? Okay, folks. Well, that is an and. This is rule, whoops. This is rule number 5. Okay, this is rule number 5. You get an A and then an A and then an A. Now remember, you never, ever, ever work directly with percents. You always change them to decimals. So we're going to take the first test, 0.50, times the second test, 0.40, times the third test, 0.30. Okay, when I multiply those together, believe it or not, ladies and gentlemen, I am only going to get 0.06, which is 6%. Yikes. You only have a 6% chance of getting an A on the 3 tests. Okay, same thing with the projects. It is an and, it is rule number 5. So I'm going to multiply the 0.70 and the 0.20 together. And so in this case, your chance of getting an A on both of them is 0.14 or 14%. Okay, getting an A on all of them. Okay, well, I could just take my 0.06 times my 0.14, but I'm going to go ahead and write this whole thing out. So an A on all of them, so that would be, so I could make this shorter and just take 0.06 times 0.14, but I'm going to be stubborn and I'm going to write this out. Okay, so I'm going to multiply all of these together. And when I do that, ladies and gentlemen, it is really icky. It's now don't round here. Go with the whole decimal, 0.0084, which is 0.84%. So you do not have a very good chance of getting an A on all 5. It's less than 1%. Remember, that means less than 1%. Now, also, if you remember how percents works, let me do this. So that would be the same as saying only 84 students out of every, remember your place value? Out of every 10,000 will be able to do that. So only 84 students out of 10,000 would actually get all 5 A's. Okay? Now, here we go. Okay, at least 1 A. Okay, ladies and gentlemen, Okay, highlight this one, start. Okay, you need to recognize these. This is where we're going to use that complement rule. Okay, rule number 4, the complement rule. When you see at least, okay, at least 1A, you want to go 1 minus. Well, what's the probability of, remember, at least means 1 or more. Okay, you cannot figure out 1 or more unless you do the complement here. So you want to go 1 minus the probability that you get no A's. Remember, the complement of an A is no A. So 1 minus the probability of no A is going to give you the at least. Again, put a star by that one, highlight it. Okay, these are going to pop up a lot. So now, let's think through this. Okay, and I'm going to fill these in backwards because I'm trying to avoid some confusion that I've seen in the past. Okay, I'm going to start with the project. Okay, this project, you have a 0.20 chance of getting an A. That means you have a 0.80 of not getting an A. Okay, hope you got your volume on so you know where that came from. Okay, again, I'm just filling these in backwards. You don't have to, but I'm trying to avoid a common mistake that I've seen in the past. All right, the getting an A on this project is 70%. That means not getting an A is 0.30. Okay, getting an A on the third test is 30, so not getting an A is 0.70. Okay, see what I'm doing? I'm doing the complements as I fill those in. And then the next one is 0.60, and then the last one is going to be 0.50. Okay, so take 1 minus all of that, ladies and gentlemen, and you're going to get 0.9496, okay, or 94.96%, and we could round that to about 95%. So the chances are good you're going to at least get 1A, okay, at least 1A. That means 1 or more. All right, if you need to listen to that again, go back and listen to that again. Let's keep going. All right, so this is actually rule number 3, not number 5. So I'm going to cross that part off. There we go. All right, so remember I had talked about an extension for rule number 3. Okay, A or B. When we have a situation where the two are overlapping each other, okay? So to keep on task with what I want to do in this lesson, ladies and gentlemen, I'm going to hold off on this one, okay? So this is my A, this is my B, and then this is my A and B. Okay, I'm going to wait to do this problem until later, all right? Because I don't want to do the Venn diagrams quite yet. So let's go down here. Okay, a voter in a large city has made up the following age group. 30% are in the first age group. Okay, I'm going to do some highlighting here. 52% are in this age group. 18% are in this age group. A mayoral candidate anticipates attracting 25% of this age group, 60% of this age group, and 45% of this age group. Draw a tree diagram. Okay, here we go, ladies and gentlemen. So, forgive me, I'm going to draw a stick person. Okay, this is the voter. This is the person voting. Now, this person could be 3 ages, 18 to 29. This person might be 30 to 59. Or this person might be 60 or over. Now, we got to look at the age groups here. How many are in each age group? Well, 30% are in this age group. So 30% are in this age group. So 0.30, remember I always use the decimal. Okay, 0.50 is in this age group, 54%. and 18 is in this age group. So I got to start off with the person and how old they are. Now, this person is going to vote for somebody. Okay, they either are going to vote for this person or they're not going to vote for this person. Okay, they're going to vote for this person or they're not. So I'm going to put yes, no, yes, no, yes, no. All right, well, the chances of that 18 to 29-year-old voting for it, okay, and attracting is 0.25. Well, that means that 0.75 that they're not going to vote for them. Okay, that's not in there, but you should know that the remaining is 0.75. Okay, the next one age group is 0.60 that they're going to vote or they attract that age group. That means 0.40 is left over. And then the older age group is 0.45, and that means 0.55 is left over. All right, so the next question is, what percent of the vote will come from the 18 to 29-year-olds? Okay, so we follow that path, ladies and gentlemen. Okay, I did it in green. So that would be 0.30 times 0.25. And you multiply those together and you get 0.075, or 7.5% are going to come from that age group. Okay, what percent will come from the 30 to 59 age group? Okay, let me do that one in pink. So this age group, 54% are in that age group and 60% are going to vote for that person. So we're going to take 0.54 times the 0.60, and we're going to end up with 0.312, which is 31.2%. All right. Now, the next age group, unfortunately, I got to switch pages here. So I'm just going to go ahead and circle really quick in orange. Okay, the next age group is the 60 plus, so that would be 0.18 and 0.45. All right, so going to the next page. So that age group, 0.18 times the 0.45, and so a little over 8% is going to vote for that person in that age group. Okay, so what percent of the overall vote does the candidate get? Well, if we go back a second and we look, so this candidate's going to get 7.5 from this age group, 31.2 from this age group, and 8.1 from that age group. So we're going to add those three together. So we're going to take the 7.5 plus the 31.2% plus the 8.1%, and we're going to end up with 46.8%. So based on the last percent, should the person win the election? I hope you say no. Why? He or she, let me put it that way, he, she did not get more than 50%. Okay, they did not win the election. If there's only 2 people running, you're going to need to get more than 50%. Okay, there are some things where if you win the majority of them, you win the election, but we're just going to imagine here that this person has to get more than 50%. All right, let's keep rolling. Try not to make this video as long as the last one, but we'll see. All right, you toss a coin 5 times in a row. How many outcomes are possible? Okay, so let's think about this. Okay, I'm just going to draw circles for a coin here. So I'm going to toss a coin 5 times in a row. 1, 2, 3, 4, 5. Now remember, there's heads or tails, right? So there's 2 possibilities when you flip the first one. There's 2 possibilities when you flip the second one. 2, 2, 2. Now, this is an and situation, folks. You're going to flip, and then you're going to flip again and again and again and again. So 2 times 2 times 2 times 2 times 2 which is also 2 to the 5th power. So how many outcomes are possible? 32. There are 32 possibilities. Now, I do not want to draw a tree diagram for this one because that would be icky. That's a lot. Okay, that would be a big tree diagram. All right, so we're going to do this in a little bit different way. The probability of flipping 5 tails in a row. Okay, well, think about this. Tails, 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 tails. Okay, flipping 5 tails in a row. That's it. There's only one way. So the probability is 1 out of 32. Okay, now the next one. Flipping 3 heads in a row. Ooh, 3 heads in a row. Okay, so I'm going to work through this one. So I might start off by flipping 3 heads in a row like that, and then tails, tails. Now remember, the heads have to all be together. I might start off by flipping a tails and then 3 heads, and then a tails. Okay, again, I got all 3 heads are in a row. Or I might start off by flipping 2 tails and then the 3 heads. Those are the only possibilities I can flip 3 heads in a row. Again, in a row. Not just 3 heads, but 3 heads in a row. Details, details, details. So that's simply 3 out of 32. Okay, folks, now this next one. The probability of flipping at least 2 heads. Ooh, 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 ooh. Love this stuff. Rule 4. Complement rule. At least. As soon as I saw that, I went, ah, okay. So 1 minus the probability. Okay, at least 2. What's the complement of at least 2? Less than 2. At least 2 means 2 or more. You're not going to be able to do that unless you list out every single outcome. You don't want to do that. So the complement of that, the opposite of at least 2 is less than 2. Okay, well, I can do that, folks. Flipping less than 2 heads, well, that means there's only 1 head, right? Or 0 heads. Okay, that means 1 or 0 heads. Well, I can do that. I could go heads, tails, 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 tails. Okay, that's one possibility. That's less than 2 heads. I could go tails, heads, tails, tails, tails. See what I'm doing? Follow a pattern. Tails, tails, heads, tails, 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 heads, tails, 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 head. Or you might not have any heads. All of them could be tails. Okay, well, that's 6 possibilities, folks. So 1 minus 6 out of 32. Okay, well, 1 minus 6 out of 32, ladies and gentlemen, that's going to be 26 out of 32. Or reduce, always reduce. That can be reduced to 13 out of 16. So 13 out of 16 times, you're going to end up with at least 2 heads. Okay? All right, next one. Find the theoretical probability of reaching each room. Okay, there's a story that goes along with this, but I'm not going to read it. It has to deal with a princess. Okay, but we're not going to go through that. So we want to know just what's the probability of reaching each room. Okay, so we're going to split this up. So you notice that when we start, ladies and gentlemen, we are starting with 3 paths. So that means this path is 1/3, this is 1/3, this is 1/3. When we reach this point, now we have 2 choices. And again, if we flip, we're randomly picking. Okay, like we're using a coin to pick which path we're going to go on, or we're rolling a die to randomly pick which path we're going on. Okay, so that's 1/2, 1/2. Same thing down here, 1/2, 1/2. So wherever it splits, You need to label those. Now, to follow this first path, ladies and gentlemen, this first path is 1/3 times 1/2, which is 1/6. Same thing with this path. It ends up being 1/6. See what I'm doing? I'm multiplying because it's an and situation. Okay, the middle path, well, it's just that path, so that's 1/3. Okay, the next path, that's 1/6 again because it's 1/3 times 1/2, and then the next one is also 1/6. So what is the probability of ending up in room X? Okay, so we take the room X, we take the 1/6 plus the 1/6. There's only two paths, ladies and gentlemen, that ended up in room X. Look, the top and the bottom. So that's 2/12, or that ends up being 1/3. Don't forget your calculator. No, not 1/3. Yeah, 1/3. Your calculator can do fractions, remember. If you forgot, ask me during class. All right, so the next one, room Y, there are three paths, so 1/3 plus, or 1/6 plus 1/3 plus 1/6. Okay, that ends up being 4 out of 6, which ends up being 2/3. Okay, obviously it should be what's ever left over from room X, right? If room X is 1/3, room Y has to be 2/3. All right, let's keep going. I am already up to like 28 minutes. All right, let's keep going. Okay, suppose you are interested in studying demoralization in golf. You believe that after losing a game to an opponent, a golfer is more likely to lose the next game because he or she is demoralized. Okay, they're feeling bad, man. After losing the first game. Your experiment might consist of watching 2 consecutive games of play and observing whether a player won, tied, or lost each of the 2 games. In this case, use W, T, and L for win, tie, lost. Okay, list all the possibilities. All right, they're playing 2 games, folks. So the person might win, the person might win, lose, the person might win, tie. Okay, that's it for starting with a win. Now, what else might happen? Okay, they might tie. No, we're not eating food. All right, tie win and tie lose. Okay, so those are all the ones that for tying, to start with a tie. You might lose, you might lose, win, or you might lose, tie. Okay, now, if you're going, well, how did you know there were 9 of them? Remember, there's the counting principle. Okay, so you're going to play 2 games. There's 3 possibilities for the first game. There's 3 possibilities for the second game. 3 times 3 is 9, so 9 outcomes. Don't forget how to use that counting rule. All right, so what is the probability that the player lost exactly one of the games? Okay, well, lost one of the games would be, let's see, 1, 2, 3, 4, 4 out of 9. What is the probability that the player does win the second game after losing the first one? Okay, well, there's only one there, folks. Okay, winning the second game after losing the first game, there's only that one right there. So 1 out of 9. What is the probability that the player wins both games? Same thing, right? Wins both games, 1 out of 9. What is the probability that the player loses the second game after tying or losing the first game? Okay, well, I'm not going to pull that back up, but that is 2 out of 9. All right. Now, in your book, ladies and gentlemen, I'm going to shrink this a little bit. In your book, there's this interesting thing called Benford's Law. Okay, it's right above, well, it's problem 44. So I'm not going to spend time in this video going over it. I want you to go to problem 44. I want you to read, okay, what it says there about fake numbers and Benford's law, and then I want you to see if you can do number 44. All right, I'm going to keep rolling here because I don't want this video to be as long as the last one. And then there's some more problems that we can discuss during class if we need to. All right, so remember the odds, the answers are in the back. If you get stuck, you can go look, and I will be doing the evens with you. So I can't remember if we're going to do 44 together or not. If it's not on the list, however, I am going to probably talk about it during class. All right, let's see. Now, we're going to stop there because the next video I'm going to begin with 6 degrees of freedom, which is a PDF right above the videos. All right, so I'm going to pause right here and I will continue the next video 6.3.